integration, when applied to geometry, integration is not really a geometric idea. It's really about finding the reverse of a derivative, okay? And basically finding a bunch of tiny products, okay? And the way I can, represent it to you as a refresher is that we can show how that looks like, how it looks like taking a bunch of tiny products and adding all those products together, integrating those products in terms of geometry, okay? Geometry isn't actually what integration represents, but geometry can make a visualization of the abstract idea of integration. Integration is really about algebra and all this. But geometry shows that algebra with your eyes. It can show it with all these diagrams. Integration essentially takes a bunch of tiny rectangles. Well, that's a very bad looking, that's a fat rectangle. I mean, rectangle, not that weird thing. And it basically adds them all up. I'm not going to draw all of them. I'm not going to draw all of them. But essentially, it takes a bunch of tiny rectangles, and it takes the width as dx, okay, this very small width, and it takes the height. The height is whatever y value is at that point in the graph, okay, y value, okay, and it essentially takes a sum, like a summation of all these different y values multiplied by these various dx's, but dx is always the same. The width of each is the same. The width of each rectangle is the same, but the height keeps changing. So it's basically taking the sum. So if I were to show you how it would look like, it would be like y1, the first y value, times dx, plus y2 times dx, plus so on. It keeps going on and on and on. But if we factor out the dx, if we factorize out the dx, all we get, we don't need the diagram anymore. All we get is a bunch of y values all summed up together, y1 plus y2 plus y3, whole thing multiplied by dx. Sum it up together. The thing is, a bunch of rectangles is not accurate. You saw that there were gaps, right? You saw that there were some gaps. Now, if I were to increase more and more rectangles, the gaps would get smaller, would get less prominent. There would be lesser and lesser gaps, but there would still be gaps anyways, right? There would still be gaps. When you approach infinity, when the number of rectangles approach infinity, thus the number of y values you're going to be using also approaches infinity, the thing is, the gaps become zero. You're approaching the actual value itself, okay? It's a very abstract idea. This is the idea of limits. If you are very curious about this, it's a very interesting idea. You should look up limits. You can watch True Blue and Brown's video on it. So essentially, I'm adding an infinite number, okay? Starting from the first y value, adding an infinite number, okay? Infinite number of y's. So all the y's multiplied by this dx. And because I'm taking an infinite sum, we used a new symbol called this integral symbol, which is kind of like an S. I guess that makes sense because it's a sum, like a really weird stretched out S. So it sums up all of the y values, and essentially it finds basically the area underneath that curve, by adding up all those tiny rectangles. Okay, and you can go more into it. You can watch Shiblu and Brown's video explaining the idea of integration. And this is basically just a summary of what it is, a bunch of summing up. But what if we had to do something different? We know how to find, the area underneath the curve. That's very basic stuff. That's baby feet stuff. That's I supposed to say chicken feet. Chicken feet's the thing that you say is easy. I don't know, but I was also gonna say it's baby knowledge, but then I said baby feet, which is weird. Okay, so basically adding up a bunch of rectangles, right? And you usually, if you want to establish what bounds, you're not going to find the whole area, because sometimes it can go on for infinity. It can be infinite. Let's say this one's going to be B, this one's going to be A. It's the area from A to B. And then when you show that, show it like this. Very easy, right? What if you want to rotate this about the x-axis? Now, it's a very weird idea, okay? The idea of rotating something about an axis, rotating an area about an axis. So let's say I had an area like, let's keep it simple. Let's have an axis like this vertical axis. And I had this area of, let's say, I don't know, this, okay? And I were to rotate it around, it were to cycle around the axis like this. and thus it creates this kind of cylindrical shape. You know, when you rotate this flat rectangle, creates this weird cylindrical, oh, it doesn't look parallel, it's supposed to be parallel. It's, yeah, cylindrical shape. Essentially, when you rotate a rectangle, it gives you a cylindrical shape, right? Very easy, right? So that's the idea of a solid of revolution. You're taking a normal area, regular area, a 2D shape, and you're going to rotate it to make it this new 3D shape by rotating it around an axis, okay? And you get this new 3D thing. And if you rotate a rectangle, it becomes a cylinder, okay? But what if you have a bunch of rectangles like I showed you earlier, which apparently is very easy, but easy means baby feet, apparently, to my broken brain. I accidentally said baby feet. So you have a bunch of rectangles here approximating the area, but as you know, as the rectangles approach infinity, they become exactly the same area. So yeah, so let's say I were to stop here, I were to stop at this bound, okay, and I were to rotate them. What would I have to do? I would have to kind of treat every single one of them making their own little cylinder, right? They make their own little cylinder, right? Every single one of them. So if I were to just if I were to just analyze, weird way to describe analyzing a rectangle, staring at the rectangle. So I have this one rectangle. There's others there, but I'm just gonna look at one. When it rotates, it creates its own little cylinder, right? And how to find the volume of that cylinder, okay? The volume of the cylinder is the surface area multiplied by the width. And the width, we always remember, of the rectangle was dx, right? That means the width of the cylinder that it makes is also dx, okay? But what's the, how do you find the surface area? Okay, the volume is surface area times width. So let me just redraw that diagram again, where you have this, and this turns around, okay? You realize that the radius is just the y value, the height, right? Remember, the height of the rectangle was the y value of the graph at that point. Remember? So you can find, oops, no, wrong thing. I was supposed to draw the graph. You can find the area of the volume of the cylinder that this will spin around and make. It's going to spin around and going to return, and you realize that the radius is just the y value of this rectangle, and then the width obviously is going to be dx. Now, how do we find this volume then? So surface area is going to be pi r squared, right? Surface area of a circle is going to be pi r squared. But the r is going to be y, that exact y value at that point. And it's going to multiply by the width, which is going to be d of x. Okay, d of x. So now we have, for a single rectangle, but we need to add up all these tiny rectangles. We need to infinitely add up all these tiny rectangles, all making their own cylinder as they all spin. As they all spin around, they'll have their own cylinder of various different radiuses, all changing radii, which is the proper vocabulary. I don't know why I should have said radii. So if I were to show you how that would look like, it's taking pi y squared dx. Remember, this was the formula for the volume of a single cylinder, right? But if I'm gonna do it for all of the cylinders, it's gonna be first the first y1, and then it's gonna add up to the second cylinder, y2, which has a different y value, and then it's gonna keep adding. And you realize it's very similar to integration, right? It's very similar to how this is supposed to be a 3. Very similar to how integration had a bunch of things add up together. So what we can do to make this look simpler, we have to factor out what's common between everyone. So this will be going on for infinity, because again, same as the rectangles, infinite rectangles that make up the actual area will make it reach the actual area, adding up all these little rectangles. And thus, same for this volume of revolution, adding up all these tiny cylinders give me the actual area, an infinite number of these tiny cylinders. Okay, so basically I need to factor out the common ones, which is going to be pi and dx. Pi and dx are like common factors, and because all I have left, the thing that's different is y squared, okay? You're gonna get different y values. You're gonna get y1, you're gonna get y2, all the various y values from between the two bounds. So basically, I'm gonna be adding all of them up, infinitely adding them up. The same exact symbol for adding up all the rectangles is gonna be adding up all the cylinders with a similar logic, and all of this multiplied by pi and dx. Dx, I can just move it here because that's how you write integrals all the time. Dx is always at the right, and then you have the pi in front. Thus, this gives me the added sum of all the tiny cylinders that make up that giant solid. You see, that giant solid that is that entire curve, right? If we spin this curve around, and then we have all the cylinders being added up, we get this new kind of curve of revolution, this solid of revolution. All the tiny cylinders that add up to the proper volume is exactly that formula. So volume is equal to pi and then y squared dx. It's very similar to finding area. Area, you're just taking y times dx. It's very similar, right? This looks like pi r squared, you know, with y being the radius, but you're adding up all of these r squareds, all the various r squareds of all the various cylinders, and this one you're adding up all the various heights of all the various rectangles. So it's very similar, right? You can see this as like the height. You know, you can see area as like height multiplied by base times height. It's kind of like finding the area of a rectangle. This one is kind of like finding the volume of a cylinder, right? Which makes sense, right? You're adding up a bunch of cylinders, and this one you're adding up a bunch of rectangles, which makes sense. This makes sense. So integration is really just multiplication, but tiny things added up together. Okay, so that's basically it. Volume of a solid of revolution follows this formula: pi integral of y squared dx. Very simple. So, yep.